Hello, everyone. I thought I'd start off this class with playing a little video for you that gives you an idea of the shape of the Earth based off of the geoid. So it's uh, if the if the geoid were zero elevation, this is kind of what the shape of the Earth would look like. Basically, what you keep in mind is that the uh, a number of the areas that are shown on here, yellow areas typically means that it's a very high gravity area, whereas purple or real deep blue colors are areas with a very low gravity component. So let me play this once. So you can see, you get up into Europe, areas like that, especially where some of the mountains are, that those areas are much higher. But for example, here in the U.S., it's not quite as high of a gravity field. Um, Likewise here along these trenches, I think that's in the Pacific. Yeah, there's Australia. You can see another high gravity area there. But but anyways, you can see that uh, things are. It gives a completely different shape of the Earth. Let me stop this. So anyway, as you can see, it's quite a bit different based off of the geoid, based off of the gravity, uh, as to what the Earth's surface looks like. Let's see. I'm going to pull up some other information here now, so I'm going to pause just for a second. Okay, I've got a website up that I highly recommend that you get used to using. This is uh, the NGS, or National Geodetic Survey website. As NGS is part of NOAA, the National Oceanic and Atmospheric Agency, or something like that. I'm trying to remember what the acronym stands for. But anyway, they're in charge of, NGS is in charge of basically horizontal and vertical control, and uh, maintaining the systems, establishing the new geoids when they come out. They're also the ones that are taking gravity measurements to for the creation of a new updated geoids. The So there's a couple of the things here uh, uh, that are beneficial. There's you can post-process GPS information. It's called the Opus. Um, what it allows you to do is to collect uh, GPS information over a period of time, and then you can submit that, and it will take surrounding uh, CORS stations, which are continuous operating reference stations, that are basically their GPS antennas, and their GPS equipment that's set up at various locations that are storing the information and make them available by computer. But what this is actually a program where it will go to the surrounding GPS locations, pull the information out, process it along with the information that you submit, and then give you a result for your particular station that you're collecting. Uh, I'll try to put together a video showing, um, or I'll put together something later showing a cores or a station collection, and what it looks like with the data sheet that's sent to you on, or the report that's sent to you when you have completed that. It has a let's see here. So anyway, the cores network, it has the information on those. So for example, if you wanted to know where all the core stations are in the US, this is them. It tells whether they're GPS or GNSS, and then what the rate of collection is. If they collect the data every second, every 5 seconds, 15, or 30. But you can zoom in on this area, for example. The course stations that they have that are available is here, for example, MOSI, that's Seiler Instruments in over in Southwest St. Louis. You have the St. Clair County building. There's one there. The Madison County one's not available on the course map. It's basically it operates independently for the same with Cordy Construction and some of the others around the area. Basically, those stations don't make their information available outside of the network that they have. Basically, if you have the subscription to the VRS, the virtual reference stations, then you can access that information through that. But as far as public information, that's not available. Now, for example, if we click on the station, it says it's operational. It samples every 5 seconds. Daily is when the information becomes available. They have GPS plus GLO is the type of the information that's available, and it says the agency is Seiler Instruments that's in charge of it. Likewise, St. Clair County is the one that operates this. GPS and GLO availability is hourly, so they put the information out every hour, and it's a 15-second sampling that as to when they take their samples. This is Missouri Department of Transportation. It's currently operational every second. Its availability is hourly. You can get GPS and GLO information and Missouri Department of Transportation. So for example, you can get the site information. It shows the pictures of the antenna. It has, let's see. has coordinate information. Um, Now, the one thing to note is that this is basically uh, the station information on it. Uh, One thing that they have started putting on data sheets, and this is something that will become more and more important as GPS gets better and better. Um, the they they put a velocity uh, on the base point. Uh, Thing keep in mind that even though we think of these stations as being fixed, I mean, remember that relative to the overall Earth, I mean, they're moving. Everything's on a plate. The plate is slowly moving across the surface. It's like a piece of wood floating on a you know uh, a whole bunch of pieces of wood all floating on the ocean, all side by side with each other. And as things happen, they rub up against each other. Some may ride higher on others, and uh, you know things like that are going on. But it's a very slow movement. But you'll see that it has an X, Y, and Z motion, or an X, Y, and Z velocity. So for example, uh, uh, the velocity in X or northward, uh, uh, the basically it's moving 1 millimeter. It's a negative value, so it's moving 1 millimeter to the south per year. Uh, in this case, it's moving 1.55 centimeters to the west per year. Is a negative number. Basically, relative to the fixed coordinates that they've established, um, that station is moving about 1.5 centimeters to the west, and then upward, it's moving 0.44 or 4.4 millimeters downward per year. So over the course of 10 years, it will move basically a centimeter to the south. It will move uh, 15 centimeters to the west, and it will move 4 centimeters downward in position. Assuming that the velocity continues the same. But it basically has latitude, longitude. It has let's see here. It's more velocity information, and what these have to do is relative to different coordinate systems. This is relative to NAT 83 2011, showing the direction northward, eastward, and upward, which is a little bit different than this velocity. The let's see, type of antenna. It has let's see. Has some other ellipsoid information, things like that. But basically, it's the information on the station. The let's see. Okay, so this is a typical NGS data sheet. What it will show is the position, latitude, longitude. It has the ellipsoid height, which we had talked about earlier. The ellipsoid height, or small h with a e subscript, that it's 132.637 meters. The geoid height is negative 31.375 meters. So that means that the geoid is below the ellipsoid by 31.375 meters, which basically means that what you do is you take the ellipsoid height. So it's 132.637, and we are subtracting the negative ellipsoid value, which is 31.375, which in essence adds 31.375. So you end up getting 164.012 meters. Which is an elevation of 538.10 feet as your elevation. So keep in mind, for any kind of conversion between meters and feet, you use if you're going from meters to feet, you multiply it by 39.37 divided by 12. So that's the conversion from meters to U.S. survey feet, which is the current system that we use. So anyway, that's the information as far as the here I'm gonna let's see here. We have farther down you have state plane coordinates. So it's state plane coordinates, Missouri East. These are, and this was NAT 83 2011 position. So those are the values in meters, MT being units. Scale factor, we're going to get into scale factor here in a little bit. 0.99993930 is the scale factor. Basically, if you have a ground distance, you need to multiply it by that scale factor to get a grid distance. Or if you have a grid distance, you divide by that scale factor to get a ground distance. Convergence, this is where we talked about the difference between the grid north and astronomic north, or geodetic north. Basically, those are the same thing. It says the convergence is plus 0 degrees, 9 minutes, 31.2 seconds. Because it's Missouri East and we're basically in St. Louis, which is towards the eastern end of that particular projection, the grid north is angling to the right, whereas positive from geodetic or astronomic north. So to convert astronomic to geodetic, astronomic or geodetic to grid, you have to add 0 degrees, 9 minutes, 31.2 seconds. So that's why it's positive. The let's see. We will get into something called elevation factor. The elevation has a effect on the scale factor as well. The so here's the mapping scale factor, which is basically right here. The elevation factor is right here. To get a combined factor to convert distances from grid to ground, this is the combined factor that results. And like I said, we'll be getting into details on that later. But I wanted to point this out to you, give you a chance um, to go in and look around on that information. Feel free to look around on the site. I don't think that there's anything else on that. Let's go back to NGS home. So if you're looking for a benchmark, they have an interactive map. So they have a thing about getting started. Basically, you can zoom in on a particular area. We'll zoom in on Edwardsville. And no. Oh, here we go. Let's see. Oh, we have to zoom in on an area. Let me zoom in a little closer. Once you zoom in on the areas you're looking, then you hit find marks. And it will come up with a list of different marks. Now I hid the legend on that. Basically, these are let's see. These are horizontal control marks that are the circles like this. Let's see here. UM139. There's the identifier on it. Okay, I guess, let's see here. Yeah, because the position is shown by, it's only shown to the nearest 10th of a second on latitude and longitude. It'd be shown to quite a few more decimal places if it were for horizontal control. But you'll see that for vertical, it's 172 point, so it's down to millimeters on that. If it, so 172.494 meters based on NAVD 88, 656.92. It's described by Patrick Engineering Incorporated in 2013 as being 8.2 miles south-southeast of Bethalto. Let's see, distance from Edwardsville to reach a station along 159. Center Grove Road, go west to Center Grove Road for 1.7 miles to 157, turn right, go north on 157 to University Drive, continue north on State Highway 157 for 4/10 of a mile to the station on the left. It's located 21 feet west of the edge of pavement of the southbound State Highway 157, 14 feet east of a light pole, and 142 feet south of the center of a private entrance for 1455 State Highway 157. It was recovered in 2019 by the Illinois Department of Transportation and recovered in good condition. It's described as a flange encased stainless steel rod or rod in a sleeve. So basically it's a it's a like a cylinder with a cap. The cap has a hinge on it. When you open the cap and look down inside the sleeve, then it's a stainless steel rod that's sticking up in the center of the of that sleeve, and the elevation is taken from the top of that rod. So, like I said, that's a horizontal location. A vertical location is right here. It's Station Edwardsville. You have probably seen it, not realized it. If you've gone east out of University Drive, out of the campus. It's at the southeast corner. See, in this case, you have latitude, longitude, down to 1, 2, 3, 4, 5 decimal places below the seconds, whereas the height is the nearest tenth of a meter. So it's a horizontal location. Now there are some locations that are both horizontal and vertical that they've used GPS to obtain good elevation as well as horizontal location, and that's shown with a different symbol. Let's see. It's at the corner of Valley View Cemetery. There's a witness post that's sticking up next to it. It's basically right on the corner of property that's owned by the common corner of the cemetery and SIU over on the east side. Let's see. There are some other points here. JB 2004. These are old horizontal control points. Goes back to the days when they would set up towers and take Edwardsville Municipal Water Tank. Those are all kind of horizontal control points. The Richards bricks smokestack was one of them, but generally, if it's just a open triangle like that, then it's not a very accurate location. If has a black triangle like that, then that means it's anything that's colored in black is going to have a better position on it. And of course, we can zoom out farther and tell it to find marks. So we'll have other marks that show up as a result with going to a larger area. Up here in Elsa, there's a horizontal or a vertical control that's there. You'll notice that this one, I actually have recovered this one before. It was set by the Department of Defense in 1880. It is a bolt set in a rock outcrop. It basically in the cliff. The let's see, it says it's 4 miles below Grafton, about 440 yards below an old flour mill, which is no longer there, 242 yards below a brick building, 105 yards along the railroad, which is no longer there, below the lower end of the trestle, and in a natural rock ledge on the rock side of the bluff, a copper bolt leaded vertically into the rock and surrounded by the letters USPBM cut into the rock. So, this was set by the Department of Defense in 1880. When you click on the photographs, now no photographs found. I do have a photograph of it, so I'll have to show that to you if you have an interest in it. But it's a really cool benchmark. You have to kind of climb up the kind of a steep grade a little bit to get to it, but it's if you're in that area and you need a vertical benchmark, that's the place that you go. So let's see here. Trying to think what other information. I don't remember if I had shown you guys this previously. Under tools, they have the coordinate conversion and transformation tool. That is extremely helpful. It always starts out here in Nebraska. I'm assuming that maybe that's the population center. I don't know. But if you move this around, and then let's see here. Oh, wait a minute. I think, yeah, there's Kansas City. Move it east until you get to St. Louis. So say, for instance, that you want to know what the scale factor is here in Edwardsville. And we'll just do it right at the intersection of Vandalia and North Main Street. So you put it on there. If you hit submit, it has latitude, longitude of where the point is. Let's see, it doesn't give, we're not doing anything with ellipsoid height, but it will tell you what the convergence is at that location and what the scale factor is. So 0.99994532 is the scale factor. You would still have to figure out the elevation factor to get an overall combined factor. But yeah, the convergence is 0 degrees, 7 minutes, 56.4 seconds, 47 seconds positive. So it's to the east, to grid north. And then it has other information as well that you can look up if you need other, other types of information. But for the most part, we only worry about state plane coordinates. I'm going to pause this. I have a meeting to go to first, or for a bit here, and then anyway, this is from the webpage for Illinois General Assembly with the Illinois compiled statutes. The state plane coordinate systems that are adopted by the various states are actually codified by law, basically meaning that they are defined as to what parts of the state they apply to, and it actually has the various factors that go into what create or uh, how they are defined. So, for example, Illinois, as I mentioned on last Thursday's lecture, was is broken up into an east zone and a west zone using transverse Mercator projection, which is basically uh, it creates a long north-south map of the state using a particular meridian that it's centered on. The what so what defines the state plane coordinates is listed in um, uh, it's the 765 of the Illinois compiled statutes, chapter 225, which is the Illinois Coordinate System Act. The it goes in and it talks about the importance of the coordinate system that's accepted by NOAA and the National Geodetic Survey for establishing points on the surface of the Earth. It goes into defining what counties are in the east zone and which ones are in the west zone. So section 3 actually states, the counties that are in the west zone, and or the first paragraph here talks about which ones are in the east zone. The other ones, the next paragraph describes the counties that are in the west zone, and you'll see that St. Clair and Madison, Macoupin, Jersey, those are all in the west zone. And then let's see, goes into a definition of the name. It's Illinois Coordinate System, comma, East Zone, or Illinois Coordinate System, West Zone is the actual name that it's defined as. When you get into section 7, it goes into the actual mathematical definition of what the coordinate system is based on. So I'm going to read through this. We'll worry just about the west zone since it's since that is what is what applies to right here. But you could read through the east zone and decipher the same information as well. So it says that Illinois Coordinate System West Zone is based on a transverse Mercator projection of the North American datum of 1983, or the Clark spheroid of 1866, North American datum of 1927, having a central meridian of 90 degrees and 10 minutes west of Greenwich, on which the meridian, the scale is set as 1 part in 17,000 too small. The origin of the coordinates is at the intersection of meridian 90 degrees and 10 minutes west of Greenwich and 36 degrees and 40 minutes north latitude. The origin given the coordinates is 700,000 meters, gives the distance in feet, and y is 0 meters from NAD 83. And if it's NAD 27, it says that it's the x value is 500,000 feet and y is 0 feet. So it gives the definition of both the 1927 as well as the NAD 83 datums. The position of the Illinois coordinate system is marked on the ground by monumented survey stations established in conformity with standards adopted by NGS for second and higher order work. Such stations may be used for establishing survey connection with the Illinois coordinate system. So, so this basically is saying that this is controlled by NGS, but this is what it's defined as. Let me pause this for a moment while I get the whiteboard out, as well as pulling up some Google Earth so you can see where this is starting from. Okay, so I've pulled up Google Earth showing the state of Illinois. If you look at the coordinates down here at the lower right and have a latitude and a longitude, you'll see 90 degrees and 10 minutes west. Basically, for the most part, it puts us about where the western edge of Madison County is. So up around Godfrey, or even, well, probably closer to Godfrey than to Grafton. But that's where the meridian runs north and south, that defines the center of the projection. So all of this area would be on the west side of the projection, whereas this area from here to basically the center of the state is basically on the eastern part of the projection. But they're all part of the Illinois West definition. Also, it says that that origin part is the intersection of 90 degrees, 10 minutes west, and 36 degrees, 40 minutes north. So, so 90 degrees, 10 minutes, and 36. I'm looking up at the definition here. 3640. So right around Brosley, Missouri, or just southeast of Poplar Bluff, is where the Illinois coordinate system is based from. Now, it's just a random point. What they did is they picked a point that they were sure was south of the southern tip of Illinois, basically farther south than Cairo, and made sure that it was a point that, for the most part, was would split that western half of Illinois basically in two relatively equal, or well, equidistant east and west from this central meridian. So at this point down by Poplar Bluff, it is given a coordinate value of 700,000 meters as the X or the east value, and 0 meters for the north or Y value. So everything is defined from that point. Now, there's not a marker there or anything like that. It's basically a point on a map that it says at these points, this is what our coordinate system starts from. Also, they say that it is set at 1 part on the central meridian. It's 1 part in 17,000 too small. So that means that the scale factor is set at that point of being basically being 16,999 divided by 17,000. So the scale factor is 0.9999412 on the central meridian. What that does is it allows, but what they do is they, at the central meridian, it's sticking up above the plane of the projection. And so the distances that are measured there, it's basically the ground distance is longer, or the grid distance is shorter than the ground distance by 1 part in 17,000. The what that allows for is that basically when you reach 1/6 in from the eastern edge of the projection area, you're pretty much at a scale factor of 1. Likewise, when you come 1/6 of the area or of the distance in from the western edge of the projection, you're at a scale factor of 1 there as well. So this is something that's established by NGS in the process. And basically by defining a certain latitude, longitude on a meridian, establishing a scale factor at that point or along that meridian, then it ends up being it makes it's a mathematical model that can be worked with to figure out the scale factors in other locations. Now, the Illinois East Zone is basically, it does the same sort of thing, but it has a meridian there of 88 degrees, 20 minutes west. It's also using the same north latitude, so 36 degrees, 40 minutes north. So it's, in the case of the eastern zone, the origin is somewhere down here in western Kentucky, but that's where the coordinate values start from, and it starts from also it starts from 700,000 meters east and 0 meters north at that origin location. The just because these are the definitions of these two projections does not mean that other projections can't be used. When you get into Wisconsin, every single county now has its own projection. What the advantage of that is that each county, then the scale factor is much closer because you are dealing with a smaller area. The scale factor in that area is much closer to being 1. So you don't have the distortion in the projection that you do with covering a larger area like the Illinois East and Illinois West. There's a lot more distortion, so there's a lot more scale factor, basically being about 99 and a half or 99.995 feet grid equaling 100 feet ground measurement. So if you're going 1,000 feet, then you're talking about 9 999.95 feet there, or if you're going 10,000 feet, then you've got about half a foot of this difference in measurement. So the way that this works, let's look at Madison County for example. Since Madison County is longer in an east-west direction, then what they would do is they would use a Lambert type of projection for Madison County. What they would do is they would use as the central meridian through the center of the county, which would pretty much pass right through Edwardsville. Or I said the central meridian. That would be the center of the projection. It wouldn't be the meridian. It would be it'd be a longitudinal line, or it's a latitude line or parallel latitude that runs east-west through through the center of the county. The central meridian would run also through the center of the county, but what you would find is that over on the east side of this central meridian, on the east side, the convergence would go to the right or to the east, whereas on the west side of that, the convergence would go to the west. The areas where the scale factor would be very close to 1 would be passing 1/6 of the way in from the northern edge of the county. So it would probably be in the area of Warden or Holiday Shores. Likewise, probably just south of Troy would be the 1/6 of the area in. So through Granite City, the scale factor would be 1. And then because the county is relatively flat, I mean, plus or minus, maybe 150 feet at the most, I would think. The scale factor is probably through the center of the county is probably going to be 1 part in, I don't know, 50,000, too small. So it's going to be much closer to being 1 than as a scale factor than what the Illinois West or Illinois East is currently. The only thing you would have to define then at that point is a point where this central meridian here, where that ends up, where the latitude and longitude lines crisscross, establish a certain coordinate value at that point, and then everything is north, south, east, and west values from there. They don't use a 0, 0 here. They use a larger number so that everything stays at above 0 as far as the values. So they actually have software now. On the NGS website, they do have software where you can create projections and and basically once you create the projection, then you can upload it into your data collector. It will use that along with the Geoid to create coordinate values, and as a result, everything you do with with a total station will very closely match to what's being done by GPS, because the two systems or the two coordinate systems are so close to one another. So anyway, that's the basics that you need to know on state plane coordinate systems and projections. The so as far as the terms, that you need to make sure you're familiar with is the mapping angle or the convergence angle, which is the angular difference between grid north and geodetic north. The scale factor is the actual linear distortion between the ellipsoid distances, which that's what the plane, or that's what the projection is doing, is that it's transferring what's on the ground to the ellipsoid. And let's see. Yeah, so the mapping angle and the scale factor are the two big things. All right, let me get the whiteboard out here. So one of the important equations that you need to know is 23.4, which is determining the scale factor. The scale factor, or S, is equal to or I'm sorry, the S is the distance on the ellipsoid, or the grid distance. So that's a grid distance. It's equal to the ground distance times the R, which is the mean radius of the ellipsoid. R is a constant, which is going to be given on any information that, or you're given information that's the charts and things like that they give you on the pull down menu. It's 20,000, or I'm sorry, 20,906,000, and it's basically the mean radius of the ellipsoid. So it's R divided by R plus N, which N is the distance from the geoid to the ellipsoid, plus H, which is the elevation above the geoid. So the type of problem you might run into is so for example, problem 10, let's see this up. Yeah, so it says an observed distance of 2,640 is your distance. it says that, oh, wait a minute, okay. Yeah, it says that your 1,400 is H, which is the height above sea level. It says that your N value is negative 131.23. Okay. Crud. One thing I forgot to mention, there's one other equation, 23.5, which is um, the grid distance is equal to the a scale factor times S. So the scale factor is K. It's like script K times capital S. The uh, okay, the big thing that I want to point out to you is that this overall equation, this is basically the elevation scale factor. Whereas this is the map scale factor. So this has to do with what elevation you're at. This has to do with where you are on the projection. If you're more towards the center of the projection, then then you're going to have a smaller K value. If you are on the if you're on the outer edges, your K value is going to be above 1. So in this case, they said, let's see what else is on there. The scale factor is 0.99994. That's the K value, or the scale factor. Oh, I'm sorry, 3 nines and a 4. And it's asking for what kind of a grid distance are you going to end up having. So this is the actual distance measured on the ground, the D. The grid distance we are going to calculate based off of the elevation. The grid distance then also needs to be multiplied by the scale factor to get to the grid, the length of the grid distance from point A to point B. So the way we go about this is that first you calculate the grid distance based on elevation. So S is equal to 2640 times 20,906.00 or 20,906,000 divided by 29,06000 plus 1,400. Well, if we put in the order there, it'd be negative 131.23 plus 1400. So S is equal to So S is equal to 2640. Oops, 2640. Times 0.9999393. So the scaled distance for elevation, or um, the grid distance rather, is, or based off elevation, is 2639.83979. But because we also have a map projection, we have to determine the grid distance by taking the scale factor for the map projection times the value of S. So the grid distance is equal to 0.9994 times 2639.83979, which equals 2638 point to, let's see how many, basically 0.26 rounded. So that matches answer A, which is closest to 2638. So anyway, that's how you calculate a grid distance based off of the map scale factor and the elevation scale factor. And yes, there are practical uses to this. We will be getting more into it the next video. So